Hello everyone, and in the previous lectures we saw how to multiply matrices. That is, we talked about matrix multiplications. Now today we want to take a look at the properties that matrix multiplications satisfy. So today we talk about these properties and we will also try to prove them. So the first property that we want to talk about is the associativity property. So what does this property mean, right? So let's write associativity. Yeah. And under this category, there are two properties that a matrix satisfies. That is, the first one being that if you have three matrices and you want to multiply them, if you multiply A and B first and then you take the result from A and B and multiply with C, this will be equal to A times B into C. That is, if you take B and C first and you multiplied them and then you multiplied A from the left hand side. The reason I'm stating left hand side because in a few seconds we'll talk about non-commutativity of matrix multiplication and where their order will matter. So that's why I'm saying that you are multiplying from the left hand side. So this property, that is I, or you can say 1, this tells us that if you had, let's say, A1, A2, A3, a lot of matrices, let's say up to AN, then in whatever order you multiply, that is, first you want to multiply A1 and A2 and then you want to multiply from A3 to AN and then you multiply, that is, you stick these results together, it will be the same as if I'll just take A1 and A2 AN. So this is what associativity means, that these brackets don't matter. And the second one related with this associativity is that, let's say I have some scalar that belongs to the set of complex number, that is, I'm considering the general case, and for this k belongs to C, we write ka b is equals to a kb. This is our second property. Now let's try to prove the first one, that is, we will try to prove this one. So let's go for a proof. So again we will refer to the index notation, and so let's write what we want to prove. C is equals to A, B, C. This is the thing we want to prove. And now we proceed with the proof. So let's first go to the index notation. So I want this, notice one thing, that this multiplication here would give us another matrix. I would have written it as D. If you want you can, but I will consider this whole thing as a matrix and then I will write a component of it. So write like this, BC, and let's say I want to work with the ijth component, that is row number I, column number j. And then if you break this up, you have to put a summation symbol, let's say small k, and don't confuse this k with the other k that we discussed a few seconds earlier. This is just a dummy index, and I want to do this. And then similarly I have to break down this BC into components as well. That is, I want to decompose the component of B times C into the individual components of B and C. So how do I do that? Again, write another dummy index, KL. Notice that this is actually a double sum. So let's write it as BKL and CLJ. Now these are just numbers. They're not matrices anymore because we are working with components, right? In fact, this is also a number. So now we can shuffle them as we want. And using the property of addition, that is, addition is commutative. That's the advantage we have here. So we will use that. So I can now write this guy over here into the following way. That is, I want to sum over this case first, and then I want to sum over L, because addition is commutative. So in whichever order you work, it doesn't matter. So that's the advantage of this addition. So let's sum over these k indices. If you do that, only L index remains, and you will have AB of IL, right? And from this side you just have CLJ. And now again you just sum over the L index. So finally you have AB C of IJ, right? But this is equals to what? This is equals to just A times BC of IJ. And this is true for each and every I and j. That is, if your matrix is a n cross m matrix, your I index runs from 1 to n and your j index runs from 1 to m. And since these two matrices, that is this one, let's call it 1 and let's call it 2, their each and every component is the same, you can conclude that this thing, where these are now matrices, not the components, this is true. Proved. Similarly, you can prove the second property as well. That is, the multiplication of a scalar doesn't matter when it comes to matrix multiplication. Okay, so we are done with the associativity part. Now what we want to talk about is the distributive properties. Okay, let me erase that. So now we want to talk about, now we want to talk about distributive property of matrix multiplication. I'll just write as m dot p, or let's just write m dot m. I don't want to write the whole matrix multiplication, it takes a lot of time. So the first thing about distributive property is the following. If you have three matrices A, B and C, then A times B plus C is equals to AB plus AC. And let's try to prove it. Proof. Again, we work in the index notation. So this should give us a matrix. So we want to take the component of that matrix and see how it turns out. So write like this, B plus C. Again, you can use second brackets if you want. I'm just using first bracket for my convenience. So IJ, how do we break it down? Notice that this B plus C, they are multiplied with A. So first we write a sum over a dummy index k. Okay, it doesn't look good. So first we write a sum over k, that is a dummy index, and you write ik, and that is B plus C, k, j. Now these two matrices, they are additive, right? So you write A of ik, and how do we add two matrices? If you recall that we added them components by components. That is, just a small reminder, recall, if you had Aij